Check.
Fabio.
What's up?
Second, right? Second. Okay.
Okay, I think we can start. So before presenting the speaker this evening, I was asked to remind you that this evening there is no test for the fire alarm. So if there is a fire alarm, it is we need to get out. So this is then there will be. And then there will be a QR code at the end of the presentation. I will remind you again with a survey. So please, for those that manage to stay until the end, please try to fill the survey. Okay, so let's get to today's presentation. So it is a pleasure to introduce Professor Robert Fleischman. So Robert is a great pleasure to host him this evening here as to this second talk, but it's also a pleasure to host him at UCL. He's visiting UCL for a short period, for 3 months approximately. He is approximately in the middle of his visit, but will stay at UCL again for the next couple of months approximately. So Robert is a distinguished professor in the Department of Civil and Architectural Engineering and Mechanics at the University of Arizona in the US. He has a mixed background, including, of course, long experience in academia, but also experience as a designer in several companies in New York, in Chicago, in San Francisco, and is a member of several national committees. So his research area spans earthquake engineering in general, but with a higher focus on seismic-resistant design for precast, pre-stressed concrete and steel structures, and with a recent focus on the development of new low-damage seismic-resisting building systems, including floor diaphragms and collectors, which is one of the topics of this evening. Throughout his career, he has been PI of many research projects. His research integrated computational simulations and experimental testing with more than 30 large-scale tests. His research has been published in over 100 publications, and the finding of his research has been have influenced significantly the American Design Code. Robert has won also several national awards. I'm not going to list all of them here. I just want to highlight that he has been awarded in 2016 the Ashe Charles Pankov Award for Innovation, and the NSF in 2014, the NSF NES Outstanding Contribution Award. So without further ado, thanks again, Robert, for being here and for giving this presentation. So I leave you the floor for the talk.
Yeah, Fabio, thank you for that nice introduction and also for hosting me at UCL. I'm really enjoying my time working with you and your research team, and also thanking the Society for inviting me here today to speak. So on the topic of a low damage system that we developed using the floor system. Since I'm overseas, I thought I would start with this slide. These are the large natural hazard engineering laboratories in the United States for wind, wave, and earthquake, and I'll be focusing on two of them in my talk, the one at Lehigh and the one at UCSD. Here's the lab at Lehigh. It's the largest such lab in the United States, and just as an aside, we just completed some testing of a steel collector under seismic forces and interstory drift. It's pretty interesting testing, and there's a link to a webinar we gave on that recently. This is the UCSD shake table site. It's the largest in the United States. The experiments I'll show you today were when this was a single direction shake table. It's now been upgraded to 6 degrees of freedom. As background, I'll take you to a former project. This isn't the topic for today, but it was using the same site and with the same research team as the project I'll show you. The topic was precast concrete diaphragms, their seismic design. And in passing, I'll mention that if you're going to try to test a flexible diaphragm, even on the largest shaking table in the United States, you have to spill out about 5 meters on each side. And we recently published a paper, not on the research, but on the engineering design and performance of that outrigger sliding foundation system. And so you might find that article interesting. It was quite a challenge. But the aspect of this project that's pertinent for the talk today is actually an aspect that's not particular to precast concrete. It's the higher mode effects that control the demands on floor diaphragms. And to show this, I'll start with some shake table responses of two nominally identical structures, except one's elastic and one's inelastic. Now, the response modification coefficient, we call it an R factor in the United States, does a fantastic job of reducing the first mode response, as you see here. But it has a very muted effect on the higher modes. And this becomes important when we think about the demands on a diaphragm during an earthquake. And I'll show it with some nonlinear time history simulations of a shear wall structure, and I'll start with an elastic structure. All those dots are when the base shear was high. And you see that the center of force is very close to our accepted center of force of a first mode dominated equivalent lateral force pattern. When you run the same structure, this time inelastic, through the earthquake, you see that there are many times where the forces are high and the centroid, the center of the earthquake forces, are much lower. The implication of this is if you're using a base plastic hinge to limit the building response, you're doing a great job with moment, but you're not having much of an effect on the diaphragm forces. Because at times during the earthquake, the forces look like this. And so you end up with a situation at different floors and at different times during the earthquake, a floor may have very high floor accelerations, very high inertial forces. And you end up with a situation where the forces may be several times the design forces. So with this idea in mind, the team that did the research said, is there any way we can directly engineer this out of a building? And this is the project that I'll show you. We call it the IFAST. It's an inertial force limiting floor anchor system, and it's using the same two labs. Here's the team. I'd like to acknowledge, I don't have a pointer, but I'd like to acknowledge the two co-PIs, Jose Restrepo and Richard Sauce, at the two testing sites. We had many students, international collaborators, industry partners, and a fantastic design consultant advisory team. We would not try to create a novel system without closely involving the people that do this for real. And so here's one of our research meetings with some leading earthquake engineering practitioners at Rutherford and Shakeen's office in San Francisco. So the concept is pretty simple. To explain it, I'm showing you a typical modern reinforced concrete flat plate apartment building. And here's the ETABS model of the gravity system in the floor. And then here's the ETABS model of the lateral force resisting system. And you see that most of the mass is in the gravity system, yet what's required to carry it during the earthquake is a small amount. And so the idea here is that maybe we can separate these systems and come up with a way of improving the behavior of the structure. So the idea is to provide a well-defined strength and make sure that that strength is high enough that it isn't overcome during daily wind events. So most days of the year, or maybe almost all of this building's life, it's just a normal building. But if a major earthquake comes along, you exceed the strength and you convert the inertial forces into relative movement of the gravity system with respect to the lateral system. If you put the right sort of devices there, you can dissipate the energy of the earthquake through this connection between the gravity system and the lateral system and lower the demands. So this system, the IFAS, has the potential to reduce structural damage because you're lowering the inertial forces. It has the potential to reduce non-structural and contents damage because you're lowering the accelerations. It has because you're actually controlling the higher mode effects, you can avoid something like an unexpected shear failure where you have a high shear force at a story. And finally, if you have a vulnerable diaphragm, this is the precast diaphragms we study. This is why we studied them. That's a Northridge parking structure. You can actually eliminate the potential for failing. The main things are the top two. I do want to say that other researchers, before we started this project, had looked at floor isolation systems. Some of them are very interesting. The one on the left is trying to use the roof as a tuned mass damper. It's a fascinating idea. This is not a pure isolation system, and I'll try to show you this right now. This is the diaphragm force, design force in the US codes. It's called FPX, and you see the pattern. And for a conventional structure, the gravity system and the lateral system are linked together, so they share the same drift behavior. Here, what we're going to do is define a weaker connection. And so we use the term alpha to express the strength ratio of the connection to the design force. So you see the alpha has got to be less than 1 for this thing to work, yes? One little point, the connection we're dealing with is actually the collector. And the collector is subjected to the special load combinations with the overstrength factor, capacity design to protect it. So you might think if we go alpha less than 1, we're making it weaker. Actually, the inherent strength of a conventional system is about 3.33 when you work out all the factors of safety. So anything below 3 is going to start to have this system kick in. The other thing is that we decided to do a constant pattern, and I'll show you the ramifications of that later on. And then the last thing is that you have to recognize that since you're actually allowing your gravity system and your lateral system to be somewhat independent. You actually have an interstory drift for the lateral system and an interstory drift for the gravity system. They're not the same. So in order for this to work, there's two issues you have to deal with. One of them is that you have to limit the relative movement of the floor relative to the walls. This is more of an architectural and a mechanical issue. And so our advisory group said that they thought this could work if we were around 100 millimeters. We had thought at first, oh, you know, we can go a lot farther. And the second thing is you don't want to make the connection between the system so weak or flexible that you have an unstable gravity system, obviously. So if we look at a graphical description, a schematic, and we go from the weak connection all the way to strong, and we go from a response from 0 to max, we are directly controlling the inertial forces through the strength of that connection. The lateral system behaves a little bit different. There's a little bit of a lag because of the differences in the modes. But now the floor relative displacements, which is something that in a conventional building, an engineer doesn't even really think about, as we make this weaker, they are going to pick up. And finally, there's a little bit of lag, but if you make this too weak, you're going to have an unstable gravity system. Here's conventional design. It's over there. And our idea was to target that sweet spot right there where we get significant reduction without the penalty of too much negative effects. So with this in mind, we set out to prototype this. And I'll show you, this is our prototype. You can see here our deformable connection is a friction damper. We also looked at a buckling restrained brace. And of course, we need a moat if we're going to have the lateral system and the floor move independently. And so when you think about it, if you have a shear wall and it's a multi-story building and there's a moat, it's going to buckle out of plane. So we needed to brace it, and we used rubber bearings for that. Now, this is interesting because we chose the rubber bearings to brace the wall, but we got an added benefit in it. The proposal we wrote to National Science Foundation, we were going to post-tension the floors so that at the end of the earthquake, they would get pulled back. It turns out that the slight secondary slope that you get out of the rubber bearings brings the floors pretty close to zero. Not perfectly, but close enough that we were able to eliminate the complications and cost of post-tensioning the unbonded post-tensioning the floors to pull them back as a self-centering mechanism. So we get our self-centering through those rubber bearings. The other point is that these are all devices that are well known. And we tried to mitigate risk in the project in the 3 or 4 years we had. We didn't think it was going to work if we tried to develop a new system and develop new components. So we used well-defined components. We reimagined them in this IFAS system. So once we had the system, we did the prototype testing, and this occurred at Lehigh. And so you can see there's a portion of a floor slab, and there's a wall stub, and then we have some high-capacity dynamic actuators. Here's one of our specimens. This is the BRB with rubber bearings. So there's a pocket there. You see the buckling restrained brace. I'd like to acknowledge Star Seismic, who donated the BRBs for our full-scale prototype. The other thing is that all of this prototype development was done by Georgios Sampras when he was a PhD student at Lehigh. And he's got excellent papers in earthquake engineering and structural dynamics on all of the development of these that you may or may not be familiar with. The rubber bearings go there, and there you see it's a carbon fiber reinforced low damping rubber bearing. I'll say that the rubber, just a little bit more on the rubber bearings, it's a medium rubber, and it's, as I said, it's both to brace the wall and to bring the floor back at the end. Just a little bit on the design. The maximum displacement, 100 millimeters, controls how thick you have to make it so that you have enough deformation capacity. It turns out our full-scale prototype is 50 millimeters thick. It's got 4 layers. And then the post-yield stiffness we want controls the size of it, and it ends up being 356 by 356. And then finally, you've got to do a check to make sure you have enough adequate compression stiffness to brace the wall. Okay. I found out that my videos don't play from here, so I'm going to have to cue the room. Gabor, you can play the first video. Thank you. So here's one of our tests. We ran these from quasi-static to dynamic, as you saw. We did different loading protocols. This is the rubber bearing, and so I want you to, you can watch the LVT in the red, but if you can see here, it's a little hard to see, but if you see the black versus the rubber bearing, it's amazing how much elastic shear deformation this can do. Okay, play the video, thank you. So you can see, you know, the amount of shear strain you can get in those things. It's really fantastic. Here's the very first test. You see we're nearly at 200%. There is about 6% critical damping ratio in these bearings, but they're elastic. This is actually going through 35 tests on the same rubber bearings. And you see that we do get degradation due to tearing and debonding. But the good news is when we did the demands for multiple earthquakes and aftershocks, we had lost about 10%. So it took a lot of tests before these things degraded. Okay, here's the BRB. You can play the video. Go ahead, Gabor, you can play the video. Now, those of you familiar with BRBs know that they work harden, and so the strength of the first cycle, it grows isotropically. And you see here the gray is just the BRB before we connected the rubber bearings, and then you see the rubber bearings effect. They give it a slight secondary slope. That brings the floor back at the end. I want to point out that we don't want that slope to be too high because we're trying to control a known force, and so we really want to stay within a window. Because of this idea of the work hardening, we felt that the BRB, there's about 3 reasons we decided the friction damper was better. Dynamic versus static, but it's stable and you could use it. So let me go to the friction damper. Here's our friction damper with an exploded view. You notice that we're using double shear as what's typical. You see that there's a long slot and a thick central plate. We have shims on either side and cover plates. For the kinematics of a wall and a floor in an earthquake, where you could have bidirectional motion, etc., you really need a lot of articulation to deal with the kinematics. So we have spherical bearings on either end, and for that reason, we needed to have actually a fixed connection to have this thing stable, or it would be flopping all around. In the end, at full scale, we have to develop about a little bit over 1,000 kilonewtons. We're able to do this with 6 1-inch bolts, 25 millimeter. A325 is the standard bolt to its full pretension with standard washers. For half-scale models, we did things like machine surfaces and used Belleville washers to have a very controlled slip load. But it turned out that for the full-scale application, we didn't have to machine, we didn't have to have high tolerances, and we could use standard bolts. So that really is a cost saver for this. Here's the full-scale prototype. So the second thing, the first thing was that this thing doesn't work hard, and the second thing is it's a lot more compact, you see, than the BRB. So the architect's going to be happy that you're asking for a small pocket, or you can hide it in the floor. Here's, you can see that one of the shims. There's the central plate with the slot. There's the spherical bearing, and you can see how well it can accommodate some misalignment or motion that's out of plane. Georgia spent a lot of time looking at the shims. We tried a number of different shim materials and geometries, and we finally settled on non-metallic to avoid certain aspects and a fairly robust thickness. Okay, so those of you that don't like the sound of fingernails across a chalkboard, plug your ears here because I'm going to play a friction damper with noise. Go ahead, Gabor. Not so bad. You know, I know a lot of people here work in this topic, including the UCL people. So, I mean, it's amazing. That is the greatest energy dissipation you could have. And when you tell this to like lay people, they're like, what? What are you talking about? Okay. So, you know, we weren't perfect at first. This is a lower level, and this is a thinner shims, and we had a lot of wear. That's not what we wanted. But by the time we got to the full scale and we had really, you know, honed in on a design, look how controlled that behavior is. Now, that's just the friction damper. And, of course, it's going to, I just will say that the full scale didn't require high tolerances or machining or anything like that, and we could keep it within 15%. This is the full test, and I won't show you anything more than the results. So this is the friction damper plus the rubber bearing. And you see now the red is the rubber bearing. You've got now the gray is the friction damper. Now you've got that secondary slope. So this is kind of our Cadillac design right here. So now that we had the prototype developed, it was time to actually try to come up with an optimum design. And so for this, it was appropriate to use simple models. And so we did two-dimensional modeling. We designed evaluation structures, reinforced concrete flat plate, 4, 8, 12-story structures. And then we inserted the device in it. And so it's a two-dimensional model. Later in the project, we developed three-dimensional models. But at this point, this was appropriate. You model the shear wall, you model the gravity system, and then you model the device. And the nice thing about modeling the device is we could take the data directly from the Lehigh test. So we weren't guessing on what the device did. We had all that information. So I'm going to show you some results, the average maximums from 10 earthquakes. And we'll look at the design basis to start. But we also, in a second, I'll show you the maximum considered earthquake. And this is for a 12-story structure. And so what you're going to see is you're going to see the average of the 10 earthquake maximum response for all these different designs, from conventional, a strength of 3.3, all the way down to essentially an isolated floor. So here's the floor acceleration and the drift. The black line to the left here and here is your conventional building. This is what a typical building is going to do in the design earthquake. And you see that by introducing this system, we are reducing both the floor accelerations and the interstory drift demand. Of course, there's a trade-off, and that's here with the relative displacement of the floor and the gravity system drift. And you see that at the end, if you look at the blue line, which is the essentially isolated floor, you're at 2/3 of a meter of relative displacement of the floor, which no one's going to take except, and you've got an unstable gravity system, right? But the key thing is, if you look at these designs, which are the purple dots, you're getting significant reduction without some of the heartache of the trade-offs. So we felt that we had a pretty good optimum solution. And now, this is my favorite plot of this project. I want to say that. I want to thank Georgios for coming up with it. It's a little busy, so let me take a second to explain it to you. It's the response of this suite of spectrum-compatible earthquakes. And the first thing I'll say is that's the diaphragm force, that's the story shear, and that's the floor acceleration. And this plot is turned on its side. So the left-hand side is that's the first floor, and that's the roof. Yes? Okay? And the black is the IFAS, the friction damper version of the IFAS. The red is the BRB version of the IFAS. And now the hollow thing is the average of the max, and the peaks are, so you're seeing the average and then the peak value. And that's a conventional system. And so this is the point I was making about trying to control the floor accelerations and how difficult it is because of higher mode effects. It's not just that we're reducing the response. It's that we're reducing the dispersion. Essentially, I mean, to me, this is an amazing plot. You're taking the highest variability, which is the earthquake itself, out. You are controlling the building. And this is the most attractive thing about this system. So I mentioned the DBE. So there's also a maximum considered earthquake. And we said that the advisors said you really want to stay between 100 and 150 millimeters of relative movement. And so when you look at this plot, this plot, the x-axis is that alpha. So as you go to this way, you're going to more aggressive designs. And you see that there's a design that works for the DBE, but it has too much relative motion for the MCE. And so we were faced with this situation. We could back off to here and lose a lot of the benefit in the design earthquake and have something that worked. But we decided to keep a design out here and come up with another thing. And what that is let's have the floor stop itself on the wall. And so you could see that you could use the floor to arrest the motion. Now the problem with that obviously is that you're going to have a huge impact force, concrete spalling. That's not a solution. And so this is when we introduced a bumper element. And the bumper we modeled, and you can see it there, that we put a gap, and then we have the idealized bumper because we hadn't tested it yet. And we tried different gaps. We started the gap from the relative movement of the floor in the design earthquake, and then intermediate to the relative movement in the maximum considered earthquake. And what we found is if we went about 1/3 of the way in between, we got a situation where the design earthquake wasn't changing because the gap was bigger than the demand in the design earthquake. But you could arrest it from having too large of a displacement and not really change the accelerations and the drift. So this became our solution. Here's our prototype bumper. Thank our industry partner, Pliger. And that polyurethane itself is not strong enough to stop a floor in an earthquake. But if you put it in a steel ring, as it expands, you get triaxial compression and you get a gradual increase. It's a donut shape so it doesn't burst. And you choose the thickness for the deformation. We also tried one that had Kevlar fibers to try to enhance the energy dissipation, but it's such a quick impact that it doesn't really make a difference. So we tested it. We needed high-speed data acquisition, high-speed cameras, an impact load cell. And you can play the video. Here's a slow motion of one of the tests. Or one of the hits, I guess, because our test had multiple hits. And then here's a video. You can play it. My student, I said, make it slow so everyone can see it. And he made it slow, so we're going to be here for 20 minutes or something. But anyway, it's going to hit. You see the force deformation take off. You can see that it's gradually increasing. And then, really, this is only a couple seconds, but it sits there for quite a while. And I guess I'm doing okay on time, because it could take like 10 seconds here for this thing to start again. And then you see the hysteresis. How's everyone's day today? Okay. Yeah. All right. Well, here's the nice thing. A large-scale shake table test takes months, and it costs hundreds of thousands of dollars. So no one is in their right mind is going to do a test unless they're pretty sure it's going to work. And that's why we prototyped, so that we could know what we had going into the shake table test. So here's our shake table. 4-story reinforced concrete flat plate building. It's half scale. By the way, we enforced strict similitude for half scale on everything, but we distorted 2 things. Can anyone guess what they are? Oh, I'll tell you. The floor-to-floor height, we changed it to 0.7. Why? We couldn't find any half-scale graduate students to work in the building. So in order for them to be able to get through there without banging their head, we did that. And that takes a little bit of mapping our analyses. The other thing is, to get the tributary seismic mass, we did not reduce the floor. So the floor is full thickness. Now this brings up an important point. Look at the columns versus the floor. Any good earthquake engineer is going to look at that and say you have a weak column, strong slab situation, and we did. So we had to actually engineer that out because we didn't want to have a story collapse. Now, we use special precast elements for test repeatability. I'll show you that. And why is that? Because we didn't have enough money or time to build 2 buildings. The E-Defense, they'll build 2 buildings side by side, and it's wonderful. We had to actually test this system and a conventional system on the same building because we wanted to do a direct comparison. And so you need a building that's repeatable, or people aren't going to believe your comparison. I want to acknowledge all the companies that helped us make this, build it. it's really, I mean, tremendous donations. The industry really steps up. So, as I said, the shake table was unidirectional at the time, and we wanted to test both the friction damper and the BRB system. So we built a awfully eccentric building, center of rigidity and center of mass offset, and so this thing twists under unidirectional excitation, and we could test the friction dampers in the main and the BRBs in the. It's also the first, well, for test repeatability, we used rocking walls. So I just want to make this clear. This system does not need a precast rocking wall. It's intended for a regular shear wall to limit the damage on it. But for our testing purposes, we put the rocking wall so we could have a repeatable structure. So this is the production drawing of the wall. We used bars. In the previous test I showed you, we'd use strands. We had some problems with it, so we used bars. And you can see here, Enerpack jack pressure transducer. We use a rubber pad to extend the sandwich between steel to extend the deformation capacity. We used external embedded plates as energy dissipators for the rocking wall, those of you familiar with that. And then we had embedded plates for our IFAS, but then we also had to have embedded plates to convert it to a conventional structure to lock down the floors. And we use a precast element called the PSA. It's a threaded nut on a spring in a slot, and you can thread in dowels. So we actually connected the floor after the first phase. I'll show you that. Oh, how do we solve the weak column? We designed these precast pin columns. It's you can see it has a duct halfway from the bottom, halfway up, and then it has a huge central rebar. It was 690 MPa, so look, you know, like really high strength rebar. Number 7 at half scale. And so the way it works is you erect the first story, you pour the floor, you erect the second story on top of it, and you grout it. And hopefully these are durable and can survive many cycles as a pinned column. We had to make half-scale versions of all of our prototypes, so the company that made the full-scale friction damper made us a half-scale. It's a little bit different. We got rid of the instability. We couldn't get Star Seismic to make us a BRB of the right shape, so we made our own. So we milled some bars and we filled them with grout, and that's a very good BRB. And then we also made our own rubber bearings. So here's our IFAS structure. You see there's the friction damper deployed, the half-scale friction damper in the main direction, and then we have the BRBs, the homemade BRBs in the orthogonal direction. That's looking down at the moat, and you can see the rubber bearing is closest to me, and then at the end is the bumper. We made one mistake with the rubber bearings. Because we have this building that's doing all sorts of motions, we just placed them in there, and that had worked in the Lehigh testing. But because of all the twisting and separation, we ended up having some of them delaminate. Near the end of the testing, there was no system critical failure from it. But if we had to do this again, or use it in a structure, we would pre-compress them, and that would make that go away, because there's plenty of compressive strength there. This is the conventional structure. There's those slots. And so what you do is you put dowels. So you see here, you thread dowels in, and then you weld them to a plate, and now you have a connection. This is standardly used in the precast industry, actually, because they've got to come up with all these neat ways of connecting things. So if you understand, we did the testing with our system, and then we tied down the floors to look at a conventional system. This worked for the lower level shaking, but when we got to the stronger shaking, it was a little too deforming too much. So we put roller bearings where the bumper is to really hold the wall in place. So here's the construction. We had concrete foundation blocks, and we put the columns on there and aligned them, and we poured the floors. So reinforced concrete flat slab, and don't forget to leave an opening for the moat, cut out for the moat. We had the precast wall donated by a really great partner, Midstate, but they were working on a huge project for UCLA, their Pauley Pavilion, and they got behind on it. And I don't know if you know about like working on a table like this. It's like this telescopes or whatever. You have a date, you've got to be off. And we were on the first floor, and they said we can't have the wall when you want it. So the good thing, by then we had started to develop our three-dimensional models. So we did all sorts of stability analysis, and we determined that we could build 3 stories before the walls went in. So we relied on the inherent stiffness of the system. We got up to 3 stories, and then they brought the wall, thank God. And this was another great day. Seeing the riggers handle this like they were throwing, putting something in a wastebasket. I mean, they dropped that into that slot, and then we poured the final floor. It was really impressive. When you have precast elements, especially if they're pre-stressed, you can't turn them the wrong way, or you get gravity and the pre-stressing acting together and they explode. Really neat. 150 to 200 instruments, accelerometers, string pots, linear pots, load cells. The kinematics of the building is such that even just to measure how much the floor moves relative to the wall took multiple measurements because we had to do corrections for large deflections. Internal or attached LVDT and an internal load cell for the friction damper. We also do payload projects. When you build a structure of this size, a lot of people want to test out their roof isolation system for equipment or something like that. So Scripps Oceanography looked at their low-cost GPS for geodetic inquiry of the ground as well as the building. So they got a publication out of that. I do want to mention the students. I've done 3 of these large-scale shake table tests, and it takes a village. I mean, students from different universities, different projects come over and they work together so well. So I really want to compliment them on the great work they did. Here they are, like preparing the rubber bearings. And so here's our tests. So phase 1 is our IFAS system. You see it here, the friction damper, the VRB. Phase 2, we locked it down, and so we did a Seattle earthquake, a low-level earthquake, and then at one of the strongest sites in the United States, Berkeley, California, we did a service level, a design, and an MCE. And you notice that we have one of each. So we have an apples-to-apples comparison of our system and the conventional system, as long as the building stays similar. Then we had a phase 3 where we had these rocking walls in pockets, and we actually grouted it and made what's called a precast emulative wall with high-strength rebar. I won't talk about that, but there was a 3rd phase of this testing. Okay, so what you're going to see here is a video of the buildings here, but I would say focus on the friction damper, and this is the force deformation of the friction damper. Okay, Gabor, thank you. And so you see up top, like that's some really dynamic sliding of the friction damper. And you can see that when you have the less emphatic motions, there's a little bit more strength. So there's like a 15% difference. This is a scatter plot of every excursion during the first phase. So it's 14 tests, 14 strong motions. And you see that within a test, there's a change in the coefficient of friction of about like 0.05, pretty controllable. And though, we're not crazy about the fact that it started at around 0.3 and it's up at around 0.48, but this is, the nice thing about the friction damper is after an earthquake and a couple aftershocks, you could reset it. You also can loosen the bolts and recenter the floor if you need to, so that's another reason why we like that. Okay, so I'll set this one up. This is the bumper. So you don't have to watch this, you've already seen it. That's the earthquake motion, the table acceleration. Here's the friction damper, but there's the bumper hits. You see there's 3 bumper hits. And so when it gets close to here, I would look here to see the bumper hits. This is the wall, and the dots are the floor. You'll see them separate. But go ahead, Gabor, thank you. So we're coming close, and now we've got some shaking. And here comes the first bumper hit. This is a maximum considered earthquake. This is when this is supposed to happen. And you see that we got good response out of the bumpers. This plot actually has a lot that's interesting. The red is the relative floor movement of our IFAS system, and the blue is the conventional. So the first thing you can see is that the bumper, and it's going from a small earthquake to a medium to the big to the really big. So the bumper did not engage as it wasn't supposed to, as it was supposed to not engage in the first two earthquakes. It hits once in the design earthquake, hits multiple times in the maximum earthquake. The second thing is you see that the PSAs, that slotted connection does a pretty good job. You see very little movement in the blue line, but when we got up to the design earthquake, you're seeing that there's a little bit of deformation. So that's when we put in the roller bearing, and the black is the improvement from the roller bearing. Okay, so now, did it work? Did it work? So I'm going to show you a side-by-side comparison. On the left, on the top, excuse me, on the top is our system, and on the bottom is the conventional. Same earthquake, same design earthquake. And I want to say that we don't really have damage, so we're measuring damage by how much response there is. So the hope is that the conventional system rocks a lot more than our system. Go ahead, Gabor. So the top is ours. It's synced up, same earthquake. And you see those arrows, so you can see. Now watch on the left. Look at this rocking. And look at the top, maybe a centimeter. So what this looks like on a plot is, this is, maybe this is a better plot. I don't know. The blue is the conventional system in an earthquake, and the red is our system. I mean, look at that response reduction. That's the wall rocking, the main wall rocking. Okay, so that's the service, the Berkeley, the Seattle, the Berkeley service, the Berkeley DB. Okay, so we'd already cracked the champagne after that, and we just had to do the Berkeley MCE. I want to say something about, it takes 45 minutes to recharge the accumulators at UCSD, because a pump can't make that table move. They have to use an accumulator bank. And it takes 45 minutes. So what happens is the test is over, and the students get like terabytes of data, and they've got to look at it in 45 minutes, because if there's something that went wrong, and we test a strong motion in the building collapse, and we're on test 2 of 20, so they're going crazy. And so this is the result that we got for, remember, we'd already cracked the champagne. No response reduction at all, okay? So we were deflated, we called it a night, and we had the students go take their time and look at the data. And what we hadn't understood is that the building had gone from a primarily translational with torsional as a secondary to a primarily torsional mode. And once they looked at all the data, they saw it, but I'll show it to you with your own eyes. Okay, I'll set this up. On the left is our building, and on the right is the conventional. It is our system, and the right's the conventional for the same earthquake. It's the earthquake that is that last earthquake we just saw. That's the problem. And I want you to look at the twisting of the roof. One of my PhD students was from Nepal, and she didn't mind heights, so this is her handiwork up in a bucket, way up in the air. Okay, you can play it, Gabor. Okay, so our system's on the left. Watch the twist here. When you add the components and do the vector sum, it's over 6%. I just want to say, these columns are amazing. Reinforced concrete columns, the building would be on the ground with that sort of motion. So here's that result. And you see that early on, there's not a lot of difference in the other direction. This is the other direction, and you see that you've got tremendous twisting. And so in that last motion that we thought it didn't work, we actually had a reduction of about 10 times in that direction. So quickly, this is the condition of those concrete columns at the end of 20 shakes. And the bottom ones are the interior with the most gravity load. You can see a lot of spalling, but they all carried their load and were stable. This is another really nice plot. This is showing so at the beginning and end of every day, we did low amplitude white noise tests, broadband, to system identify. And so we started with a 0.55 second structure, and you see this is every test at the end of each day, or between each test. And you see that we did 20 strong shakes, and the period went from 0.5 to about 0.75. That's pretty repeatable behavior, actually. And what does that building get for all its trouble being so nice to us? We had to destroy it. If you do large-scale shake table tests, you better have a line item for demolishing your building, because you got to do it fast and you can't damage the table. So this is I don't want to tell you how, like, you think all the money's going to graduate students doing research. No, it's going to demolishing the building. Okay. We did three-dimensional modeling, we calibrated it, and we used it to do all sorts of virtual tests. I do want to point out that there's work ongoing on this. This was a few years ago we did these tests, and I encourage you to go to George Sampers's website and see the work that he's doing. I showed you the students that I'm so proud of. 4 of them are professors now. That's fantastic. He's one of them. He's at UCSD. He had been at Lehigh. And also, people that aren't involved in the project. Larry Fonestock at University of Illinois came up with this frame spine system. And it was great, except they had really high accelerations. And they put force limiting devices, and the acceleration goes from 2G to 1G. He's got a lot of really great publications there in the blue, and I encourage you to look at this very interesting work that they're doing here. So in conclusion, this system shows the potential of significantly lower drift demands and hence lower damage, lower accelerations. The friction damper or the BRB with proper articulation are cost-effective solutions. I didn't talk about this, but we had originally thought about a ledge configuration to carry the gravity load. It's so hard, how do you measure that friction? So this moat is very nicely controllable. The rubber bearings provided the stability and elastic restoring forces. The bumper device limited the relative displacement, and we developed models. So here are our publications. We're still working on a few, and with that, I thank you for your attention. Yeah.
So thanks a lot, Robert. I don't know if we want to start with the questions. We do have one question online, so I will start with that. Yeah. Okay. Yeah. Go ahead.
Ian Smith from Atkins Realis. Thank you so much. That's a fascinating presentation, quite at speed. So I was particularly interested. My use of rubber bearings has historically been on bridge decks, where you've always got the vertical compression and not really in a seismic region. So when you're actually sandwiching them between your shear wall and your deck, how do you actually locate them? Are they actually bolted to both parts? So because when they shear, they tend to reduce in height normally, which isn't a problem for a free surface. But when they're in a gap,
well, we did have. So I'll say we had embed plates, and we had edbed bolts and oversized plates that we could then attach.
Yeah.
But when we did the testing at Lehigh, we were pretty much doing it kind of straight ahead. And we did, after a while, start to get some degradation due to maybe opening. And so we kind of didn't get that right in the shake table test because there was a lot of articulation. And so our idea is that we would make them slightly larger than the gap.
Yes, that's all I'm doing.
And pre-compressed. So we needed to talk to you a number of years before we got the shake table because we missed that idea. Yeah.
No, fascinating. Yeah. Thank you very much.
Thank you.
Other question? Yeah.
Thank you. Colin Morrison, now retired. Thank you very much. Very impressive set of research. My question is whether that moat approach is really applicable into real buildings, where you then got to have a floor that's going to have architectural use and services, etc., etc.
Yeah.
Have you thought of that? Or has any, when you're doing a trial like that, do you put a few pipes in or a bit of false floor and see how it would behave in those circumstances?
Yeah, really, really important question, which I kind of skated over. Let me say that a real issue is fire protection, right? I mean, you have an opening there, so you have to deal with that. We originally had a ledge idea, and the idea was to have it on a ledge, but the whole beauty of this system is the control. you're controlling everything and trying to control, it's the coefficient of friction between that surface, especially when there's some sort of overturning, you're not going to get good control. The seismic design consultants thought that the moat system would be able to be taken care of. That if this ever got built, which it hasn't been yet, much to my slight dismay, that they would come up with ways of like flexible couplers for the pipes and that sort of thing. And that's why they wanted to limit the motion. They thought that would be fine at every floor. And I get what you're saying. Like, is someone going to want to run pipes through that opening, and then you're going to have them squashed in an earthquake?
I think perhaps you need a deep false floor and a deep false ceiling, and you have all sorts of overlapping things that are non-structural and at the moat are sacrificial.
Yeah, that's true. You could actually fill the moat with something that would give way during the earthquake, or you could have a second like false floor, false ceiling to take care of those ideas. Yeah.
Yeah, I mean that's fine so long as it's low enough stiffness that it doesn't affect the dynamic geometry or the stiffness.
Yeah, that's true. I mean, like, someone puts in an infill wall and messes up your
you fill a fire with foam, but it's sufficiently stiff that it modifies the properties.
Yeah. Well, I mean, we had our hands full getting to where we got here, and these are questions that we're hoping if as we get the word out, if it gets adopted, people will come up with ways. So I appreciate your comment. It's a very important part.
Yeah, that's the next step when it becomes real.
Yeah, that's right.
Thank you.
Thank you.
Christian Malaga, thank you very much for a very, very nice presentation. I really enjoyed it a lot. I think I'm not understanding something. For the MC earthquake, you have this torsional, but you have still not deactivated the other, right? So you have the BRBs acting in the perpendicular direction, and the friction devices still acting in the other direction, right?
Yeah.
So why is it that you get no reduction, or you get a very minimal reduction on the response there?
The best way I can explain it, and I don't have a complete answer for you other than we noticed that this is what happened, is that before then the predominant motion was translation, and so we were getting a reduction. And what we were seeing in that last slide is that the translations were similar because it wasn't the dominant motion. The dominant motion was a twist. And yeah.
But you see my point. You still have the devices acting and the design acting in that direction. You didn't disconnect that, right?
We got tremendous reduction in that direction. So
in the perpendicular one.
Yeah, it worked.
Yeah.
Yeah. What I was showing is that once we looked at the twisting, the conventional one was twisting a lot, and the BRBs were
working more.
Yeah.
Yeah. Okay. So what was your distortional mode? What order had it in your initial analysis?
Yeah, I mean, I think I don't remember offhand, but the issue is that you're no longer on the elastic modes of the structure. So,
yeah.
But I don't have
and it's a rocking system anyway. So.
Yeah.
Very, very interesting. Thank you.
Yeah, no, great question. Let me find out that it's been a number of years since we looked at that, but looking at the modes of the structure would be important.
Other questions?
Hello, my name is Andreas Nilsson, and I'm also with Atkins Realis. I have a sort of maybe a very simple question, which perhaps stems from my inexperience as an earthquake engineer. When you decouple the lateral load resisting system, as you do from the floors, the lateral load resisting system ceases to be able to carry any gravity loads. Is that correct?
Yes.
Yeah. Is that conventional practice in the design of earthquake resistant buildings, or would it not? Is it more common that that these shear walls also carry gravity loads?
There are what we call bearing wall systems and frame systems. You can have it either way. There's always some gravity load on the lateral system. These walls are carrying their self weight, but there's cases where engineers actually try to mobilize gravity load to a wall to kind of actually reduce its response. There's situations where axial force on a concrete wall is really problematic when it gets too high, and so they try to move it out. So it's a little bit of different things. But we didn't want to actually cantilever a slab to the wall. We tried to do a ledge at first where we actually put and it turned out that it was problematic. So it's something that has to be designed for, and it's not completely typical that a wall's only carrying its self-weight. That's a good point.
Right, okay, so that means you need more columns then at the end of the day for the gravity system to carry the floors.
I mean, you have to modify your design because you're redistributing the gravity load to other places, but whether you need more columns it's not clear. Yeah.
Right, okay, thank you.
Yeah, it's a really good point. You know, I just want to say we didn't really think about the difference of the lateral system, the effect of pulling that gravity load off. We were kind of thinking about the system. So that's the second point that I'm going to go back and look at our stuff. Yeah, thank you. Yeah.
So I would move to the questions online, or at least we alternate one question from home and one from here. So there is one question from Elena Elettore, UCL, so which refer to the plot that you have for the mu, the ductility, versus the cumulative displacement graph. So I'm going to read the question. So which phenomena can explain the variability of the friction coefficient observed in the mu versus cumulative displacement graph recorded during the experimental campaign?
Yeah. I think that Georgios will answer this a lot better in his paper because he was closely involved with it. But I believe the reason was what he called a break-in phenomenon, where that you would start to wear the surface and you were causing extra friction as the shims were wearing out. That was the idea. That's why the coefficient of friction was changing. But again, it was gradual enough, and that was over 14 tests, that we feel you could use this and then upgrade it for the next, if you thought you were going to get a second earthquake at the building. Thank you, Eleanor.
Other questions from the room? Yep. Yeah.
David Hawthorne, Geological Survey. Thank you for a great talk. This is almost certainly a question born out of my ignorance as a non-engineer. But with your damping joints, do they have a fixed life expectancy? Would you modify that based on a certain level of shaking? Would you expect to have to change them after a big earthquake?
Yeah, very good. Okay, good question. So let me start by saying this is inside a building. So that really helps because it's a controlled environment. So you don't have to worry about temperature dependency of the rubber bearings and that sort of thing. The second thing is with the shims, I think Georgios decided to use a composite shim because he was worried about some sort of long-term, galvanic effects or something like that of having, different metals being squeezed together. We've never gotten to the point, if we actually built one of these, we'd have to have an inspection protocol. The nice thing about the friction damper is that it's going to survive the earthquake, and then you can inspect it and replace shims or whatever, retighten bolts, etc. I don't know if I answered. Yeah, okay. Thank you.
So I think we go on with the following question online. So this question is from Mohamed Kuset. So based on your analysis from the DB and MCE, when you use MCE in the nonlinear analysis, how do you exactly apply it? Do you multiply the ground motion by the factor, or is there a combination involving soil PGA or other factors?
Yeah, I think it was a straight like 150%, and then straight 150% on that. We matched the design spectrum and then scaled. I'm almost certain on that. Yeah.
Okay, thank you.
Thank you.
No, not yet. So if there are, we'll answer. Otherwise, we'll continue the discussion here.
Yeah, okay. So, thank you. I'll ask another question, if I may. So, Ian Smith from Atkins Realis. You mentioned the benefit of the slightly sloping hysteretic climb,
Yeah.
and I didn't fully understand what was making that climb. You know,
Oh, okay. Yeah, sure. It's the rubber bearings.
It is just those.
Yeah, the rubber bearings actually were designed so that when they went through the shear translation, they would have a certain slope that would keep the force within a window, so we were controlling it, but when it let off, would bring the floor back close to the zero position. So you think about if you're on ice skates and someone pushes you, you're just going to go. So anytime you don't have a restoring, even a small restoring force, you get tremendous, there's nothing to stop it, basically. So that's the purpose of that. And yeah.
And was that a special feature with the bearing procurement that you needed, or was it just a characteristic of laminate?
We designed them. That slide showed that
Yeah.
Georgios actually had this in mind, that
Yeah.
he was going to make sure it didn't fail in the expected motion, and then it provided the right restoring, and then we checked the compression. But I do want to say that it kind of fell in our lap, because our original proposal was that we would unbonded post-tension, like rubber bands,
Yeah.
that when the floor got out, we would pull it back.
Yeah.
And there's all sorts of complications with that you can probably imagine. And we were able to just completely forget about that, because when we started doing the analyses, the rubber bearings showed that we put there to brace the wall were actually giving us the restoring we needed. Yeah.
That's great, because the actual strain that you've got so large, is that rubber starts to tear at those sort of strains, but it didn't, and it really performed.
Well, we made the lamination total stack long enough so that, and we have that bumper, so it can only go so far. So that was all engineered. Yeah.
Brilliant.
Yeah.
Thank you.
Okay. I do have some questions as well.
Uh-oh.
So, no, so the first one is, have you considered the possibility of including high damping rubber bearings instead of coupling the rubber bearings with friction devices or BRBs? It seems a perfect system just to include the rubber bearings there.
Yeah, we didn't look at that. I don't know if they would have enough strength for what we wanted, and so I think we might end up having a really good dissipator. Maybe it would be like less complication under the floor, but possibly we wouldn't make the displacement. But I'd like to talk to you more about that.
No, I mean, of course, the friction devices or yielding dampers are those that dissipate the most energy.
Yeah.
So, of course, a high damping rubber bearing will dissipate less, but it's a viable option as well. Then another thing that I was interested in is, I guess that one of the key parameters is the relative stiffness between the wall and the structure, right? Because, of course, you want the wall to deform a certain amount and the structure to deform a certain... Yeah. Did you define any rule of thumb, let's say, in order to design the two systems?
We did I can kind of answer that question. We started looking at almost like the equations from Der Haag or whatever for the tune mass damper, you remember? And tried, and it ended up being that the thing that's operating the most on this system is the strength. And so other than some stiffness that would be out of bounds, it wasn't that sensitive to the initial stiffness. We looked at it for different gravity systems. We looked at flexible gravity systems, more stiff gravity systems, and in our parametric work, we were able to show that there were differences, but it worked within that. But I think the strength is the most important thing, and the stiffness is less important because, once you hit that cap load, it really didn't matter that much. If that answers your question, yeah.
Yep. Damian, please.
I Damien Grant from Arup. Yeah, just I was sort of thinking along similar lines to that last comment, and in particular, wondering the extent to which, if possible, from those kind of numerical studies you were talking about, if you can distinguish how much of the reduction effect is just due to the sort of fuse that you're getting at that location versus the energy dissipation you're also adding into the system.
Yeah.
Would you get the same if you had a nonlinear elastic hysteresis loop? You wouldn't get the benefit.
You wouldn't get that. That's right.
Okay.
You would end up exercising the bumper too soon. So
sure, but you'd presumably get a lot of that benefit by capping the amount that can be transferred through that.
Yeah. Yeah. Well, we are in our system. We're allowing the wall to have some limited yielding, so it's not staying elastic. I mean, not in the shake table, but yeah. And so we are getting like reduced energy dissipation out of that. And I don't have I'm sorry, I don't have the number. These questions are amazing. I don't have the number offhand of the percentage of energy dissipated by the device versus the rest of the system. And we also tried to model the gravity system somewhat accurately, because it's going to be going through some drifts. And so we had different hysteretic models for reinforced concrete and for steel. So we are getting, obviously we did that for both the conventional and, so we weren't, doing something unfair. But I need to go back. That's the third thing. Fourth thing, to go back and look at that, because that's a very important parameter that I don't have at the top of my head. Yeah.
And actually, sorry, just while I've got the mic, you're talking in response to Ian's question about the self-centering. It has the propensity to self-center when it has that post-yield stiffness, but of course it doesn't necessarily self-center in the way that a big elastic band would do. Was it essentially zero, or was it?
Yeah, it didn't.
Small.
They didn't come back to zero, but they came back to the position where, I'm thinking like a quarter inch, something like
small,
that.
Very small.
And so the thinking was that if you needed to, you could unbolt and try to use jacks and push it possibly, or something like that. But it just it wasn't worth. I mean, why would you put a unbonded post-tension system to move the floor that much at the end of the
Great, thank you.
Yeah, please. No, not so far.
Sorry to bother you again. I was interested in what you just said about the bumper in response to Damien's question, that although it's an elastic system, essentially the rubber bearing translating, having a non-linear system means you start to decouple it from the ground motion. Did you notice that at all on any of the cycles? Because if the bumper, you showed that curve as the bumper came in, and that's really valuable because that changes the local behaviour in terms of the period at that moment in time versus the ground motion. So I just wondered if you noticed any of that in the response.
Yeah, well, we actually have a paper that we're working on because on the bumper, and I think this gives me a really good idea that the dynamic characteristics with and without the bumper is something that we want to stress at that situation. We also have we had accelerometers around the bumper on the shake table test, so we might be able to put simulation and experimental together on that. I don't have an answer for you today.
Yeah, thank you. Interesting.
Yeah. I do have another question, which is about the variability of the periods of the frame during the last test that you show. So you show a variability that was in the order of 0.55 to 0.75, but after each test you could see that there was in some cases a period reduction. So, if you can comment a bit what is the cause of the period elongation, and also what were the operations that you were doing, in between tests to, let's say, repair the structure so that was causing this reduction of the period to the level similar to the one of the original structure.
That's an excellent. No one's ever asked that question, and you notice that it was sawtooth. So The period elongation that occurred in each test was because we were damaging the structure. It was getting sicker. The mass was kind of staying the same, and the stiffness was going down. But we would take a measurement at the end of the day, and then we would get there in the morning, and because of the marine layer and the tests and everything, we would look at what the pressure transducers would reading, and so we would re-tighten the post-tensioning. We would look at the friction damper and possibly do some tweaking on that. I think probably those are the two things that we adjusted, and that's why we have a little bit of a recovery each time. Trying to think if there was anything else, but I think that might be it. Yeah.
Yep.
That's a good point.
No, but that's usually a very good indicator of the reparability of the structure. If you can so easily recover the initial period of the structure and the initial stiffness. Yeah. Is there any other question? Andreas?
Yes, just one more question, if I may. You have your favorite slide, which shows the very stable response you got with your new IFAS system, and then you saw a huge dispersion in the, I think it was the shear force in the lateral load resisting system with conventional design. That dispersion, that huge variability in shear force, was that from testing or was it from analysis?
That was from analysis, but those were the individual results of each earthquake. And so when you look at the coefficient of variation of everything possible that goes into the pot when you're making an earthquake situation, the biggest variability by miles is the earthquake. And our system is kind of agnostic to the earthquake.
Yes, and that's a very impressive result. But it also shows then that if we decide to go for a conventional system, how can we be sure that we capture the appropriate design force in the lateral, in the shear wall? If it's so variable, how many analyses do we need to do with spectrum compatible motions to ensure that we capture the full range? And do we just design for the mean, or what do we? This is not precisely the topic of your presentation.
Yeah, but there's a whole field that deals with probabilistic dynamics, and there's arguments about this, how to scale the motions, and there's accepted ways of taking a mean and a standard deviation or two, etc. But I guess what I want to stress is the place where they really dropped the ball, where this effect really made a difference, was on floor diaphragms, because there's high variability of the force, and it's just that most structural systems have enough redundancy and overstrength that they were masking it, and then these precast parking garages with these long spans with these connections that were out there with no redundancy, they paid the price. So that scatter kind of gets diluted for other responses if you're looking at what's happening at the bottom of your wall. But that variability is something that all structural engineers designing a conventional structure for earthquake engineering are factoring in the confidence level that they have based on the variability.
Thank you.
Is there any other question? We do have one more question from home. So, thanks for the outstanding presentation. I'm wondering if you ever considered replacing ADAS components instead of rubber bearing.
What was similar to your question, or?
Yeah, using ADAS component.
Oh, the ADAS. Oh, yeah. No, I'm glad you said.
Yeah.
My proposal to the National Science Foundation had unbonded post-tensioning and ADAS devices. And the Lehigh team started working with it, and they said, it doesn't have the it doesn't have the strength and deformation that we need, and that's when they looked at the BRB and the free damper. So I did. That was my idea. Was the ADAS. That's where I got that. Yeah, actually, Jose had done. This is Jose's idea. He had done some small shake table tests, and it was maybe it was the TDAS. He had done like miniature shake table tests and had seen promise, and then we wrote the proposal. But yeah, our original idea was the ADAS. I forgot all about the ADAS.
Okay.
That's a metal damper for those of you that don't know about it.
I don't know if there is any other question. Otherwise, I would thank a lot Robert for the excellent presentation and the answer to the questions.
Thank you.
So I would like to thank, on behalf of SEGED, also everyone that has participated to the talk. I was told that there exactly. So there is a QR code. If you can please scan it and do the survey. Should take no more than 2 minutes. Okay, I did it as well. Yeah, so I think we can conclude this event. Thanks a lot, everyone, again, and also including people from home that attended the event.